So it is the 31st of August. We've made it more than halfway through the first week. And we left off talking about conversions, of course. So how many of you have done any work with the conversion practice sheets? Okay. Like I said, there was one typo on the one. It should be minutes squared, and it shows as meters squared. On the back, it's not a typo. So anybody have questions on the bigger batter? The thing that I didn't get to discuss with you is when you're doing a conversion that is a derived unit, such as grams per cubic centimeter, meters per second, the easiest way to set that up, and I'm just going to do a very fast one here. If you're going 15 meters per second into kilometers per hour, factor label gives you a fantastic way to do that. If you make sure that your units are where they would be. Don't put meters per second all in the top box, because then what you tend to do is not know where your meters are going to cancel. So then you can do, if we're going to kilometers per hour, you can do 10 to the third meters, 1 kilometer, and you can do this all at one big shot. 3.6 times 10 to the third seconds is equal to 1 hour. And it makes it pretty fast and easy. The ones with derived units are the ones where people tend to trip over their own feet. So doing that, making sure that you split those derived units is one way to avoid making that particular mistake. And if you practice those, if you're, when you check the key, you'll see my work on them. So that's just a little helpful pointer from somebody who's made every dumb mistake you can make. I can help you not make the same ones. You can make your own new dumb mistakes. Many of you have heard about accuracy and precision and have talked about it in physical science and maybe in chemistry and someplace else and remember anything about it. Okay. It's important, in the lab that you just did really kind of gets at that issue of accuracy versus precision. Accuracy is being correct. You know that. It's getting the true value of something. Precision is more related to the instrument you're using, and it's more about the ability to make repeated measurements that come out the same every single time. I always say of the balances that we have here in chemistry, they seem to be fairly precise. They are not all that accurate, and if you switch balances between part 1 and part 2 of a lab, your data is just wrecked, because you can get the same precise measurements on a thing with one of those balances again and again, but they vary widely from instrument to instrument. If you were using a piece of string cut to length, it's not a real precision instrument, because one person may hold it more tightly, one person may hold it more loosely, there's stretch, there's slop, and it's a source of error. So what you end up with is an instrument that's not terribly precise. You might get an accurate reading, but it might just be dumb luck. This is the standard illustration, goodness, it's printed in everything, on distinguishing accuracy from precision. The goal is to be accurate and precise. That's the best of all possible worlds. If you're not precise, it's hard to tell if you're accurate. You got a bunch of values, and gee, they averaged the true value, but if you don't know the true value, you have no way of knowing that. So if you're using a precision instrument and you're using the instrument well, hopefully then you're getting precise and accurate measurements. And of course, if you're neither accurate nor precise, all hope is lost. Abandon hope, all you who enter here. Let's talk about error. Woo-hoo-hoo. Why do we get inaccurate readings? Because we have error. And some error is your fault and some isn't. So there's method error. Take two measurements with different methods. Perhaps you have recently experienced this. In a lab setting. Making measurements with multiple methods. That can lead to inaccuracies. And again, if you're not using precision instruments, you never know which measurement is inaccurate if you're getting different measurements. Also, just being sloppy. I'm a little bit of a woodworker, and I fight against my own tendencies. Measure twice, cut once. Care in making measurements, not rushing measurements. Because when you rush, you tend to make mistakes. And this last one is parallax. Do you know what parallax is? I know it says thumb shift eye wink, but that's not what it is. Parallax is a difference in perception of the location of an object based on the perspective of the viewer. So, I would invite you all now to experience your own parallax. Take your thumb and close one eye and cover up some object in this room. It can be somebody's head, it can be the clock, I don't care what it is. Now, keeping your thumb out at full distance and covering up that object, switch the eye that you've got open. Oh, look at that, your thumb jumped. And you can play with that, you know, you can entertain yourself probably for 15 or 20 minutes that way. I can anyway, but I have low standards. That is because your eyes are in slightly different positions. The further apart two observers are, in this case the observers are your right and left eye, the larger a difference there is in the position of the perceived object. Astronomers actually use parallax to measure distant objects by taking measurements from observatories on different parts of the globe. And there's all kinds of math that is way above my pay grade that goes into it, but based on that, you can actually determine how far away something is, based on how much the image shifts its location, based on how far apart the observers are. Now, that said, I've been saying for years that I have an exaggerated parallax distortion. So when I measure things, and I know for a fact, medically diagnosed, my eyes don't work together quite as well as everybody else's. So I can't look through a microscope with two eyes, which every prof I ever had in college wanted to beat me up for. I can't do it. They don't work together correctly. So when I'm taking measurements, I cannot take a measurement with both eyes open because I see two images. And if you are in that boat, if you have to take measurements with one eye closed, make sure you're consistent, because otherwise you introduce your own form of parallax error. This is what I blame most of my sloppy measurements in woodworking on. Oh, it's my parallax error, but who knows. The other source of error, so you know, that first group method error, that's pretty much your fault. That's pilot error. You know, you didn't pay attention to your method, or you used a couple different methods, or you know, you closed the wrong eye. Then we have instrument error. And damaged instruments give you instrument error. So this meter stick is relatively new and in good condition. We have lots that have the ends busted off and wound down and worn down from years and years and years of Beaver local students, not only making measurements with, but whacking them on things. I tend to start my measurements at the 1 centimeter mark for that reason, because the ends get worn over time and it's a source of instrument error.
Please excuse the interruption.
Okay, so you know, watch for damaged instruments. We don't do as much with balancing, using the balances in here, but occasionally we do. Sometimes we have a scale that won't balance, so that's an instrument damage thing. The other issue is faulty instruments. One thing that we do use quite a bit in here are spring scales for computing force, or for measuring force. And they look like this. You probably use these in physical science. It's, you know, the same thing that you might weigh a fish on. Real simple device. But if that spring gets damaged over time, you now have a faulty instrument. So you want to make sure, if the instrument, you know, if the spring gets stretched out or kinked, I've seen a few where, oh, actually, oh no, okay, that's fine, where the spring has been damaged in some way, and then it's going to give you an inaccurate reading, and it's an issue of instrument error. Those are fairly self-explanatory. Precision is all about your instrument. Precision is all about your instrument. When you are taking measurements, you are responsible for the level of precision in the numbers that you are getting. And you guys did a good job with it. We talked about it a little bit during the lab. You can always take one more digit than the last increment on your instrument. I really hammer this in chemistry, and you know, you have to go one digit further. You've got to go one digit further. What's interesting then, there's a particular lab we do typically sometime in December, and we use the spring scales. Now we have 3 different 3 or 4 different types of spring scales available. We have some that are 2.5 Newton spring scales. I'll take a picture and insert it. So we've got these 2 spring scales, and you'll notice right off, hopefully, that one of them is not calibrated, one of them isn't zeroed, and there are ways to zero them, there are ways to calibrate the instrument. So if we were using this, we would want to check to make sure it was calibrated first. But the other thing I want you to look at is the fact that the scales on these give you radically different numbers of sig figs. So on this one, which only goes to 2.5 newtons, the last increment is 1/10 of a newton. So if you're recording a value on this, all your values should go to the 100th place. So you should record values like 1.10 newtons, 2.55 newtons. On this one, it only goes to 1/2 a newton. So that's 1, and the last increment is 0.5 newtons. So you can't go any further than that. It presents a challenge because, of course, the difference between 0 and 0.5 is what? 0.25, which is actually 1 more sig fig than you've got. So you'd have to go like 0.3, because you can't go out another digit. You just can't. So on this, you would be recording values like 2. Let's see, if we get a value in there, 2.5, 2.8. That's as far as you can go. You can't go that additional level. Okay. That one's a little tough because it's not marked in an even tenth, so it's not a specific place. That's where you have to pay close attention to the precision of your instrument. And whenever we're doing labs, I will come around and ask you pesky, irritating questions about the instrument that you're using so that you make sure you're recording your data correctly. Okay, so page 17 summarizes the rules. Brief recap: if it's not a 0, it's significant. There are special rules for zeros, and I'm not going to go through all of those right now, but we will work on them. Not much, though. I kind of expect when you get to physics, if you have had chemistry, that you've had these, and we'll refresh and review, but you are responsible for sig figs pretty much from day 1. When we are doing calculations with sig figs, there are special rules. Let's talk about those. In general, if we are adding things, our sig figs are limited by the decimal place in the number with the least places, with the least precision. So we would be limited to the 10th place. So though our raw answer for this is 2.25, we're limited to this place. And based on this number, we're going to round up, so we're going to show the answer as 2.3. In multiplication and division, we are limited by the thing which has the fewest number overall. So though the answer to this is 10, please, if you haven't already, look at the practice for conversions. I will put up, I'll link some sig fig practice from chemistry. If you want to look at it, fine. If you don't, fine. See you tomorrow, guys.